Hey folks, this video is going to be probably kind of long because I'm going through three examples of Newton's second law for circular motion. So on Edpuzzle, you're going to have the ability to skip and basically like tell me when you're done with it. So there's three examples of using Newton's second law for circular motion. And I just hopefully with these examples, I'm just going to show you some of the things you would expect to see when asked about circular motion. And these are all circular motion on Earth. When we cover orbital motion next, we'll talk about circular motion in space. So the first one is an apparent weight question. So we have a car driving over a hill at a constant speed. The hill is about approximately circular and has a radius of 60 meters. At the top of the hill, what is the apparent weight of the car? So there's some like concepts here. So the hill would look like this. The question you're being asked is when the car is at the top of the hill. So we covered this in like free body diagrams, and then the center of the circle will be like somewhere down there. So let's like look at a free body diagram and then talk about the question. The car, it doesn't really matter what direction the car is traveling in. The free body diagram of the car is going to have a normal force pointing up and a force of gravity pointing down. So I think in general in circular motion, you want to be careful about when you assign like the horizontal forces. We often don't need to. So the car's like coasting, and so we kind of imagine that there's no horizontal forces. Because it's going at constant speed, even if there was a horizontal force, there would be two opposite ones to keep it going at constant velocity. So for our purposes in AP Physics 1, it's actually best to like not worry about any, for the most part, like horizontal forces when something's moving over a circle like this. Okay, so back to the question. At the top of the hill, what is the apparent weight of the car? If you remember from the dynamics unit, apparent weight is asking about normal force. In other words, how heavy would the driver of that car feel when they were at the top of the hill? And what I want you to understand is that this problem is just like the elevator problems. Something's moving in a circle now, but it mirrors the example of the elevator perfectly. When the elevator is at the top of its path, whether the elevator is like slowing down to stop at the top floor or starting to descend from the top floor, it perfectly mirrors this because the acceleration of the elevator and the acceleration of this car is downward. And so in this case, it happens to be centripetal acceleration. In the elevator, it's linear acceleration. And that's really the only way that they differ. So when you're faced with an apparent weight question, it's always about the normal force. And kind of the understanding here is because the acceleration of this car is downward, so it's traveling in a circle, it has to therefore have centripetal acceleration. Because that acceleration is downward, our understanding immediately is that the force of gravity is going to be greater than the normal force. Because the acceleration is downward, the net force acts downward. And so the downward force has to have a greater magnitude than the upward force. And so we're just going to show how that works mathematically. What we're going to do is start our centripetal net force equation. Because this is circular motion. There's only one dimension of forces here, so we're just going to leave it alone at the centripetal direction. Because the acceleration is downward, I'm going to go force of gravity minus the normal force as the net force expression. So the positive direction minus the negative direction. That's something to get used to in this unit because it always used to be like up minus down and right minus left. But now I want you to kind of force it to be whatever the positive direction is minus the negative direction. And then as far as like mass times acceleration, because I'm given the speed and the radius, I'm going to substitute in, instead of centripetal acceleration, v squared over r, just because in this situation, we're given variables that are related to like speed and radius. And I could calculate acceleration, but I would rather just put everything in at once. As far as the algebra for this goes, I would add the normal force to both sides, and I would subtract mv squared over r from both sides. And so I would get the force of gravity minus mv squared over r. This is mathematically showing what we understand conceptually. Because the net force is down, gravity has to be greater than the normal force. And in the expression, I have the normal force is equal to the force of gravity minus the net force. And so that's like mathematically proving that that is true. As far as like substituting in variables, I will leave that off of this video. We've done a lot of substituting variables in right now, but the force of gravity is mg, net force is mv squared over r. You will get a normal force of approximately 4,700 newtons. Now, 1,500 kilograms is the mass of the car. If we say that little g is about 10 newtons per kilogram, then the weight of the car is 15,000 newtons. So this is like a little bit under a third of the weight of the car. It's probably a little bit above just because I'm rounding, but this is significantly lower than the weight of the car. So, if you go really fast over a hill, you're going to get that like feeling in your stomach like you do when you take a roller coaster ride, where you feel light and it feels like your stomach is like churning a little bit. Okay, so next question is about a skateboarder. And so this is another normal force question. And so we're just going to work with this one. So again, like you can like skip around here. But this question is about a loop-the-loop. And so the skateboarder is going to be in the loop. And I'm just going to draw it as like just a complete circle, just for simplicity's sake. And there, the skateboarder would like head into the loop and go over it and then come out the other side. We're just going to treat it as if they're a circle. Derive an expression for the minimum speed necessary at the top of the loop to prevent the skateboarder from falling. So the first thing you want to latch onto is you are about to analyze the skateboarder at the top of the loop. So that's their location. And it really doesn't matter what direction they're moving in, but that's their location. The center of the circle is underneath them. So this is very similar to the problem we just did, because the circle, the center of the circle is underneath the object that we're thinking about. This free body diagram is going to be a little different. I'm going to draw the skateboarder as a box, and you'll see why in just a second. As far as the forces acting on the skateboarder, we again make an assumption every time it's circular motion that it's constant speed. And so any left and right forces will cancel. And so what we really care about are those vertical forces. Well, in this situation, we have the force of gravity on the skateboarder. And then because the loop is literally above the skateboarder, the normal force also points down. So something that you don't have to do this, but when you have when you kind of know you're going to have multiple forces in the same direction, I sometimes like to draw the object as a box just so I have more space in my diagram to show my work. So that's the start of this problem. So I'm going to pretend that we don't know what to do next and take a look at the problem. Okay, so we have the radius of the loop. Derive an expression for the minimum speed. Okay, so radius and speed are the two variables that are kind of, we know are involved here to prevent the skateboarder from falling. Well, so that's kind of tricky. This is like totally new. So why don't we start kind of the way we're always going to start these questions, is with Newton's second law. So we have speed and radius, and so we have this idea of acceleration. Now, the acceleration of the skateboarder has to be downward. I mean, that makes sense with the free body diagram, because only the only forces we have in our diagram point down. But also because the center of the circle is underneath the skateboarder, they have to be accelerating toward the center of the circle because they are moving in the circle. So for this, the net centripetal force, well, I have to add these two forces. So it's the normal force plus the gravity force equals, And then again, because like radius and speed are variables that are mentioned in the problem, I'm gonna, instead of just leaving it as acceleration, I'm gonna substitute in v squared over r. Okay, so a couple things about this. The question says derive an expression. And so this has to be your first move, is to write out a physics equation that is very general. In other words, it's something that basically comes off your equation sheet, and that's where you start. So, you know right now that we're in the middle of like Newton's second law for circular motion, so you like should start with that equation pretty much, and that's your thought process. Derive means you're going to work symbolically to figure out an expression that ends in v equals, right? So determine the minimum speed necessary at the top of the loop to prevent the skateboarder from falling. So let's kind of look at this equation and break it down. And this might be this is what makes this video long, but minimum speed necessary to prevent the skateboarder from falling. Here's the concept. If the skateboarder goes really, really fast, they can't change their weight because that's constant for where they are, but they can change the normal force. And so what I want you to see is the only variables that can actually change in this equation are the normal force and the speed. Everything else is absolutely constant in this problem. So you can't change the skateboarder's mass, you can't change the strength of gravity, can't change the radius of the loop because it's probably made of like concrete, and that's it. So the only thing the skateboarder can do is control their speed, and according to this equation, that's going to influence their normal force. So if you look at how the equation is set up, these two things have a direct proportion. As the speed of the skateboarder increases, the normal force increases. If the speed of the skateboarder decreases, so does the normal force. The question says, what's the minimum speed necessary? And so if we take this to its conclusion, the lower the speed gets, the lower the normal force gets. At a certain point in time, the speed is so low that the normal force wouldn't even be there because mv squared over r would be equal to mg. So in this situation, mathematically, we want to see what the speed is when there's no more normal force. The learning you take to future problems is if something falls off of a surface, well, that means that there can't be a normal force. So the moment you're looking for is the normal force, or rather the speed is so low that there is no normal force. Those of you who have studied limits in math class so far are probably going to have an easier time kind of accepting this. You're kind of like finding the lowest speed such that like as the normal force approaches zero, what does the speed approach? So I guess in the heart, this is a calculus question, but we can still apply our idea. If we set the normal force equal to zero, that is the moment that the skateboarder actually starts to lose contact with the loop. And that's kind of our magic moment there. That is going to show us what the minimum speed would need to be in order for the skateboarder to not actually fall. So our equation becomes mg equals mv squared over r. And so what you are going to notice is that the mass can be divided out of this equation, and we get g equals v squared over r. If we are looking for the minimum speed necessary, if I solve this for v, I get the square root of g over r. And so whatever the radius is, the square root of g times r, that represents the minimum speed the skateboarder could have to not fall from this loop. Now, there's like a dose of reality there. They could probably be going a little bit slower, and what would happen is like they would lose contact with the loop and they would fall, but they'd probably like hit the loop there. So they could like recover from it, but lower than the speed, and they would actually lose contact with the loop right there. Okay, so that's two concepts involving normal force, either what is the apparent weight, or basically when does the thing lose contact. This last one is about friction. And so the question is, what is the maximum speed with which a car can make a turn around a curve of radius 20 meters on a level road without sliding? And so again, like I'm gonna try and deal with this conceptually, and then show you how to work with this. So as far as this goes, for a car driving on a road, we want to act like we are behind the car. So this is like the view from behind the car. And before you even draw anything, you want to identify where the center of the circle is. In other words, if you're like following behind the car, do you think the car's about to make a left turn or a right turn? And just because most things in physics we want to have happen from left to right, I'm going to say that the center of the radius of the turn is to the right. So if you like, if you think about like the rotary by Camp Curtis Guild and REI and the Wakefield Lake, you travel around in a circle. And the center of the circle is the center of the rotary where no one can drive. It's like underneath the highway. That's what I want you to think. If you're just taking like a regular right turn, maybe from like Main Street onto Birch Meadow Drive, then the center of your circle is like where the crossing guard stands as he waits for like kids to walk up and hits the button. So it's like a location that's off the road, but it does represent the center of a circle. So what happens when you take that view is you have the weight of the car, you have the normal force on the car, and those are in the vertical direction. And so then the idea becomes there has to be a horizontal force that points this way. And so the idea is, in order to drive a car, you have to maintain the force of static friction. The force of static friction has to be strong enough to hold the tires on the road. And the force of static friction can only point in like one direction at a time. And in this situation, as soon as you turn your wheels, you are actually changing the direction of static friction. It can point in more than one direction, but you are causing it to at least partially point off the road toward the center. The way that I want you to think of that is if you start to turn your tires and you lose traction with the road, your car just goes in a straight line. And so the friction force is the force that's going to cause the car to move in a circle. That static friction force is going to point approximately to the center of the circle, and that is going to represent the net centripetal force. So the acceleration is always going to point toward the center of the circle. And in the case of a car on a flat road, it's the force of static friction that's going to point the acceleration toward the center of that circle. There are, so that's like the diagram. Now let's like get an equation up here, and then we'll deal with the concept of maximum speed. So in this situation, you've worked with friction a little bit, so you might know that you're going to need two net law or net force expressions, because you remember that the force of friction is equal to mu times the normal force. And so so friction is going to be in the centripetal direction, normal force in the y direction, so you're probably going to need those. You get that mu, and so that's like your hint. So well, we have to deal with this now. What is the maximum speed with which a car can make a turn? The implication of that phrase is if the car goes any faster, it's going to start to slide. So not only is this a static friction problem, but it is a problem involving the maximum value of static friction. So anything mathematical where you are going to need to do Newton's second law and something with static friction, all of those problems have to be for the maximum force of static friction so that you can use it as an equality instead of a less than or equals to. So let's set up some equations and see what we have. In the y direction, we have normal force minus mg equals 0, and therefore normal force equals mg. This is so far no different from what it's always been. Again, this doesn't happen all the time, but it happens most of the time. In the centripetal direction, we have the static friction force equals mv squared over r. So again, I put in v squared over r, especially because we're being asked for speed and we have the radius as a known value. And so the next step is, I only have the radius. I don't have the mass of the car, and I definitely don't have the force of static friction. So as from like a problem solving standpoint, what I need to do is like derive some more. So we've done this before. If the normal force is equal to mg, then the static friction force is going to be equal to mu mg. Because we are using the maximum static friction force, and so it's mu times normal force, which is mu mg. So I substitute, and I say static friction coefficient times mg equals mv squared over r. And so I have an expression now that I can work with. It got mu in there. Mu is a known value. I got g in there, g is a known value, and I can divide out the mass. And so, it happens with a fair amount of frequency that when you're dealing with friction, the mass just cancels. So we have this expression, mu g equals v squared over r, and this speed is going to be equal to the square root of mu times r times g. It should look to you very similar to the last expression from the skateboarder problem, except now we have mu involved in there. So, your answer, if you plug in the numbers, ends up being 14 meters per second. But kind of like back to the concept, if we stop here, we say like, okay, well, this is a finite value. This represents the maximum. So maximum static friction force. And then this represents the net force associated with it. Now, as the car speeds up, the net force on the car increases. So the car can be going like 10 meters per second. And if it's going 10 meters per second, then static friction, because 10 is less than this number, static friction will be able to keep up with that. It will exert less than its maximum force to keep the car stuck. Once we get up to 14 meters per second, we are pushing this equation to its limit. If the car were to go 15 meters per second, then the friction force needed to keep the car going in a circle wouldn't be enough to keep up. So this speed represents the maximum speed you could put in here to equal the maximum static friction force. Any speed above this, the car starts to slip. Any speed below this, everything's fine. It's going to stay still, or it's going to stay static friction on the road. So that's like the limit of that. So that's 3 examples. There are like several more that you could encounter, but that's just kind of some general ideas. Thanks.